Welcome back to differential equations. In this video, I want to talk about convolution. Specifically, I'm going to be looking at how convolution interacts with the Laplace transform and how we can use convolution and the Laplace transform together to solve differential equations and initial value problems. But before I get into that, a quick primer in convolution. I think it is very likely that most of you have never come across convolution in a previous mathematics course. The idea of convolution is very useful in two unrelated branches of mathematics. Signal processing and its close neighbor image processing is one place where convolution is very common, and probability theory is the other place that commonly sees the idea of convolution. For our purposes, we're not going to worry about the hows and whys, we're just going to look at the what. Convolution is an operation on functions. Most of the operations you're familiar with, adding, subtracting, multiplying, dividing, are defined for numbers, and then we carry that over into functions. Some of the operations you're familiar with, integration, differentiation, are unary operations affecting only one function. Function composition is an operation that you've seen in the past that acts on two functions, combines two functions, and there's no analog for that in the world of numbers. Convolution also falls into the same category, although the definition also will involve an integral. Let me get my head out of the way and let's jump right into that. If we have two integrable functions f and g, then the convolution of f and g is denoted f asterisk g, right? The convolution of f and g, f convoluted with g. I've heard a couple of other ways of phrasing it. Again, that's not really the big idea here, but it is a function, and in order to talk about it, we're going to need to have the independent variable, and I'll use t. That's very common in the work we are doing with initial value problems. The integral from 0 to t, right? So a function defined by an integral integrates starting at some starting point. 0 turns out to be very useful, going to the value or the independent variable, the value where you are evaluating the function. And then I'm going to take my function f, I'm going to evaluate it at some dummy variable. I'm going to use tau here just because I need something to fill in, and it kind of looks like t. Then I take my second function g, and I evaluate at t minus tau. And then I'm going to integrate with respect to tau. So remember, for a definite integral, the variable that you are integrating over, we sometimes call a dummy variable because you use it to figure out what you are doing. You integrate over a region, and then after you're done performing the integration, the dummy variable is gone. So we can call this thing whatever we want. Tau is one option, there are others. The important thing is that we can use it and we can perform this integration. So as a seemingly simple example, I would like to take t and convolute it with e to the 2t. Well, from our definition, this is going to be the integral from 0 to t of my function f, which is t, evaluate that at tau, and you get tau. Then my function g, e to the 2t. Replace t with t minus tau, and integrate with respect to tau. How you continue from here, you have a couple of different options. I think the way that I like going about this is to start with a u substitution and get that stuff in the exponent a little bit simpler. Currently, it's a bit of a mess. I'll also let you know that if you look ahead in the process, we're going to be doing some integration by parts. So having u and v available would be really nice. Right? So I don't want to use t, I don't want to use u, I don't want to use v, I don't want to use tau. I need some other letter. I'm going to use xi. I really like xi, and it doesn't get used often enough. All right. And I'm just going to set that as the exponent here. 2 times the quantity t minus tau. And I can distribute that out, 2t minus 2 tau, which will actually make things helpful for us. Because one of the things we're going to need, I've got a tau hanging out by itself here. So in order to perform this u substitution, one of the things I'm going to need to do is solve for tau, right? 2t minus xi over 2 in this case. Another thing I'm going to need to do is figure out the value of xi when tau is 0 and when tau is t. So xi of 0 is going to be 2t minus 0, which is just 2t. And xi of t is going to be, well, 2t minus 2t, which is just 0. And the last thing I'm going to need to do is differentiate dxi. Well, remember here that t is a constant in this integral. We're integrating over tau. So the derivative of 2t is just 0. The derivative of minus 2 tau is minus 2 d tau. So with all of that substitution, I can rewrite this integral as the integral. When tau is 0, xi is 2t. When tau is t, xi is 0. Tau is 2t minus xi all over 2. E to the 2t minus tau is e to the xi. And d tau is negative 1/2 dxi. A little bit more cleanup here. Remember a property of integrals. Taking the negative of a definite integral changes the limits of integration. So I can take that negative and use it to rewrite this as the integral from 0 to 2t, which is more the shape that we are accustomed to seeing. I can take the 2's here and combine them together. So I've got 2t minus xi over 4, e to the xi dxi. Oops, a little too far. This is a much simpler integral than the one we had before, but it is still a very complicated integral because you have two things being multiplied together. So from here, I'm going to integrate by parts. Specifically, let's let u equal 2t minus xi over 4. Let's let dv equal e to the xi dxi. And the reason I chose this is that when I differentiate 2t minus xi over 4, it's going to become something simpler. And when I integrate e to the c dc, it's going to become no more complicated. The integral is very straightforward. Integral of e to the something is that just saying e to the something. Differentiating is not that hard, but do pay attention and remember here that t is a constant, c is a variable. So differentiating 2t gives me 0. Differentiating minus c gives me minus 1/4 dc. Then from there, integration by parts formula. The integral u dv is u times v, 2t minus c over 4 e to the c. This is a definite integral, so we carry our limits of integration, 0 to 2t, minus the integral, still 0 to 2t, of v du. So e to the c minus 1/4 dc. How you continue from here is a little bit of personal preference. I'm going to leave this first bit as limits to be evaluated. And integrate the second bit first. The integral of e to the c is e to the c. And then I can evaluate. When I plug in c equals 2t, well, I get 0. Right? 2t minus 2t is 0. Multiply that by 1/4 e to the 2t, I still get 0. When I plug in 0, I get 2t over 4 e to the 0, which will reduce to 1/2 t, but I'll leave it like that for the moment. The second one is a little bit easier, e to the 2t, e to the 0. So I've got negative 1/2 t. I've got 1/4 e to the 2t, and I've got minus 1/4. Right. The aestheticist within me says that this should be 1/4 e to the 2t minus 1/2 t minus 1/4. That is an order that is more familiar to mathematicians, but that's not something that really matters all that much. So again, the application of convolution in signal processing, the application of convolution in probability and statistics are two interesting ideas that are beyond the scope of this course. If you are going in either of those directions, you can expect that convolution is something that you will see quite a bit more of in future courses. For right now, all I care about is that it is an operation we can perform. It's not necessarily a fun one, but it is one we can handle. That's good enough for me. The reason I've said I care is I want to see how this works around the Laplace transform. I claim that the Laplace transform of a convolution is the product of the Laplace transforms of the two functions. Proving that isn't necessarily difficult, but it's not really much fun either. And so instead of proving that, I'm going to go back to the result we just concluded. The convolution of t with e to the 2t is 1/4 e to the 2t minus 1/2 t minus 1/4. We know from the work we've done previously that the Laplace transform of 1/4 e to the 2t minus 1/2 t minus 1/4, we can evaluate separately. So we'll have 1/4. The Laplace transform of e to the alpha t is 1 over s minus alpha. So in this case, s minus 2. The Laplace transform of t is 1 over s squared. And the Laplace transform of 1 is 1 over s. Cleaning this up just a little bit, we've got, let's find a common denominator. It looks like it's going to be 4s squared s minus 2, which means this first thing needs an s squared in the numerator. The second thing is going to need a 2 times s minus 2. And the third is going to need an s and an s minus 2. And if we clean all of that up, let's see, that's s squared minus 2s plus 4 minus s squared plus 2s, distributing everything out. And s squared and minus s squared cancel each other out. Minus 2s and plus 2s cancel each other out. 4s cancel each other out. So we get that the Laplace transform of t convolute with e to the 2t is 1 over s squared times s minus 2. And if we try to use our theorem, remember that the Laplace transform of t times the Laplace transform of e to the 2t is 1 over s squared times 1 over s minus 2, which is in fact the same thing. All right, so it's not a proof, it's not mathematically proving that this will work for everything, but it's a nice verification of the result, a nice little bit of understanding and seeing that this is going to give us the same thing either way. But as has been the case with the Laplace transform, the thing we really care about is looking at integrals. So let's get all of this out of the way and let's take a look. All right, let's get my head out of the way first. Then we can look at an initial value problem. This is going to be a very simple one. We definitely could solve this initial value problem using the tools that we already have at our disposal. But I think that is a great place to start. We use the more powerful tools to solve problems we already know how to solve. And that way, when we get to the problems that we don't know how to solve, we're already comfortable with using these tools. All right. So y double prime minus 2y prime equals 0, along with the initial conditions y of 0 equals 0, y prime of 0 equals 1. I could definitely solve this using the method of characteristics. It wouldn't even be that challenging. But if I try to solve this using the method of, using the method of Laplace transforms instead, well, the Laplace transform of y double prime minus 2 times the Laplace transform of y prime is equal to the Laplace transform of 0, which is just 0. And the Laplace transform of y double prime is s squared times Laplace transform of y minus s times y of 0, which is 0, minus y prime of 0, which is 1. Laplace transform of y prime is s times Laplace transform of y minus y of 0, which is 0. So I get the Laplace transform on y is 1 over s squared minus 2s, which means that I can solve this by finding the inverse Laplace transform of 1 over s squared minus 2s. And this is not an inverse Laplace transform that appears on our table, but you may and hopefully did pretty quickly recognize that there is a common factor of s between the terms in the denominator. So we get here that y is the inverse Laplace transform of 1 over s times 1 over s minus 2. And each of these are Laplace transforms we recognize. The Laplace transform of 1 over s is 1. The Laplace transform of 1 over s minus 2 is e to the 2t. And so if we perform the convolution, 1 convoluted with e to the 2t, that should give us our solution. I'm running low on time, and I've hit everything that I really needed to hit. So to wrap this up, I would like you to evaluate this convolution. Easier than the one that we just finished, but still something interesting. 1 convoluted with e to the 2t. And if you have the time and inclination, go back to the initial value problem we just solved. Use the method of characteristics to solve that using the techniques we've talked about before, and verify for yourself that you get the same result either way. In any event, that's all I have for now. So take a few minutes, see what you can do with that. I'll see you in the next video.